Now in this video we will see the design of a belt. Now for that we need a PSG data book. So this is our PSG data book, and here we are going to study with the design. Now let's start with it. Now in numerical it is given that the belt conveyor system for a specification: number one, troughing angle, that is 20 degree, material to be conveyed, that is coal, capacity it is 200 tph, that is tons per hour, lump size it is 125 mm, then inclination 15 degree, and center to center distance it is 90 meter. So these things are given to you in exam also. So if one of the thing is missing, then you have to assume it as a standard one, like troughing angle or center to center distance, inclination. But generally these are the mandatory things to design the belt conveyor system. So let's start with the solution. Now the assumption, it is assumed that the loading is taking place at the tail pulley and unloading is taking at the head pulley. So as you can see, there is a head pulley, and here somewhere we will get a tail pulley at this side, and there is one more drive pulley. So head pulley is generally a drive pulley, the tail pulley is generally driven one, but sometimes both are driver only, but here in this case there are two driver pulleys. Now as you can see it here, the material is going to be put it here, and that will be conveyed on this belt through this row, through this conveyor belt, and it will be fallen down with the gravity, and then the belt will be moved in this path, and the same process will be repeated. So this is regarding the loading and unloading of the material. Now this is a general diagram. While designing the belt conveyor you have to draw it. As you can see it here, we have rollers, the troughing rollers, and here we have return roller. Then here we have carrying idlers, we have already seen that. Now let's start with the actual drawing. Now the given data, the material it is of coal. The material is of coal. The Q value, that is capacity, that is 200 tph tons per hour. We have 125 as lump size, inclination 15 degree, length is 90 meters, total length is 90 meters. Sorry, the distance between two centers is 90 meters, and the troughing angle it is 20 degree. Now let's assuming 10% extra load or 10% extra capacity, that is we have Q value is 200 tph, we have added 10% extra, that we will get 220 tph by adding 10% extra. Now we know we are going to use a coal as it is mentioned in the numerical only. So for that we have to first calculate the density here. So for that density you need to go to PSG 9.28, sorry 9.22. So this is correction. So we have to go to PSG 9.22 for density. So let's move to PSG 9.22. So this is PSG 9.22, and we are going to find out where is the coal. Now as you can see it here, for the coal we have value of 0.7 tons per meter cube. So here we have a coal value from mine, and it is 0.65 to 0.78. So here we have assumed it as 0.7 tons metric cube. So this we have taken, it is on PSG 9.22. Now once we got density of value, then we are going to calculate for belt width. So for belt width we have two formulas, one is from PSG data book and other is empirical relation. Now this is the empirical relation, now which is equal to B is equal to X into A max plus 200. So this you have to remember. Then X value for the graded material we take 3.3. So 3.3 into 125, it's our lump size, plus 200, that will become 612.5 millimeter. Now this is the value we got it from the empirical relation, but there is one more formula which is in a data book which calculates a minimum value, the minimum value of belt width. So that is on PSG 9.18. So let's move to PSG 9.18. So this is PSG 9.18, and from here we are going to get the value of B minimum. So here at the down we have value of B minimum. As you can see here, B minimum is equal to 1.11 Q upon CV raised to power 1 by 2 plus 0.05, where T1 is the maximum tension in the belt, B is width of standard belt, then I we are going to take it from PSG 9.21, and here the working tension of the belt 1 millimeter width kg per mm per ply. So here we are going to check for, actually it is for F value. So first we will go with one by one value. Now first, where C is the factor for type of idler, that is 460 for troughing angle, which is 20 degree. Then V is equal to that belt speed, we have assumed it as 2 meter per second. Now density is known to us, C value is known to us, V value is known to us. So from this we can calculate B minimum. So B minimum, it is 0.704 meter. Now the thing is, if we convert into centimeter, it will be convert into millimeter, it will be 704 millimeter. And the initial, it was 612.5. So out of these two values, we are going to select this 704 millimeter. But this is not the standard value again. So we have to go with the standard width of the belt, and which we can take it from PSG 9.19. So as you can see there, here we have standard width of the belt. So on PSG 9.19, we have the standard width of belt. Here we have 400, 500, 650 and 800, and last one is 1000. So we are going to select 800 because we have 740. So we will select 800. So we have selected 800 width as a standard for the belt. So once we have selected 800, we will keep that value over here in this formula, and in reverse way we are going to calculate the actual speed. So what we have done, it we have used the same formula. Here we have kept B is equal to 800 mm, and we have calculated velocity of the belt again. Now the next step, it is of drive unit. Now we know we need to get with the motors that how much load will be on the motor and which motor we should select. So for that we have to select drive motor. Now the providing driving traction required for moving the belt and load. A drive unit consists of a motor, gear reduction unit, a drive pulley and couplings. The drive should be capable of moving the belt at a constant or a variable speed according to the requirement. Now we are going to move to the page number 9.18, and where we are going to get the values of resistance on the belt. Now here as you can see the formula PSG on PSG 9.18, on PSG 9.18, that is the resistance on the belt on the top of run, that is W0 on conveying up, is given by. So here on PSG 9.18 you will see this W0, and these are the formulas that we are going to use it. Now first we will focus on WO, W0. So this is the formula, that is CFL in bracket GG plus GB cos delta plus GRO plus H in bracket GG plus GB. Now here we are going to see one by one values. What are those one? So this we have taken from PSG 9.18. Now in this, where C is the secondary resistance factor, which is 1.8 for 90 meter from the graph. Now here there is one graph on PSG 9.18. So if we'll check it, so this is the graph. So on this graph we have to check it for 90 meter. So here somewhere we have a 90 meter and the value is of 1.8. The graph is not that much clear, so there is one more graph, you can download it for this from the internet, and from that you can calculate it. So from this graph, for L is equal to 90 meter, uh, the value we have taken is 1.8, which is somewhere here. So after getting the value from here, that C is equal to 1.8 from PSG 9.18 only. Now next we have value of small f, that is friction between idler and belt, that we have taken 0.02 for standard conveyors. As you can see it here for F, the friction between idler and the belt, here you can see 0.02 for standard conveyors, so we have taken that value, so 0.02, so this is 0.02. Next L is given 90 meters, so that we have written. After that we have GG and GB. So for GG and GB we have to find out the values. So as you can see it here for GG, here this is the value of GG, the weight conveyed material meter per length. So actually here we have Q weight, that is 220 tons per hour, and next we have 3.6 into velocity, that is the formula we have to remember, and from that it is 40.21 kgf per meter, that is actually weight conveyed by it. Now after that, the next value, it is of GB. So GB is weight of belt meter per meter length. So here we can find it out from PSG 9.19. So if we go to the PSG 9.19, now here go to table 1. So this is table 1. So it is given average weight per meter run kgf. So here for 800 we have selected 12. So this is the 12 kgf from table number 1. Now next we have GRO, that is weight of troughing idler on the top run per meter length. And next after that we have GRU, that is weight of straight idler on the bottom run per meter length. The tube diameter, it is 140 mm and the bearing diameter is 20 mm, 25 mm, that we have assumed it from table number 2. So just we will check for it. The maximum spacing of the idler is 1.5 meter and the maximum spacing for straight idler, it is 3 meter. So it is, we are going to take it from PSG 9.19 table number 2. So if we'll check it, this is the table number 2, and from here we are going to check for the values. So we have selected 800 as a standard belt width. Now after that we can select tube diameter and we can select bearing diameter. So in that we have assumed it the tube diameter as 140 mm and the bearing diameter is 25 mm. So after selecting that, as you can see, here we will get 27.4 and here you will get 18.8. So these values we are going to check it. Now the next one is the maximum spacing of straight layer is 3 meter that we have taken from PSG 9.19. So let's see that. Here we have table number 2. So here we have table number 2 again. This is table number 2 and the maximum spacing, as you can see it here, the maximum spacing for idlets. Now for that, here we have a written idler, so it is given 3 meter and it is equal for all the distances, so we have 800. So for that 800 we have 3 meter only, so we have taken 3 meter. Now next we are going to calculate for a GRO. Now for GRO we are going to get the value of data from the data book, that is from table number 2 and page number 9.19. Similarly for GRU also table number 2 and page number 9.19. So let's move to the next page, which is this. Now this already we have done it, the values of it. So GRU it is 27.4, so already we have taken this is GRU value 27.4 divided by spacing. So here it is 6.26. Now next we are going to calculate for height through which the material is to be lifted, that is h. Now h is given by L sine alpha and N sine delta, and 90 is our total length, and sine delta that is inclination. So inclination is 15 degrees, so it is 23.29. Okay, so similarly GRU you can take it from here, that is 18.8. So here we have taken 18.8 divided by space, that is 6.26. Once we got the values of GRO and GRU, next we are going to calculate resistance on the belt on the top run, that is W0, the total value. Now we have all the values, and from all the values we can calculate this W0, that is 1438.53 kgf. Now similarly we are going to calculate for resistance on the belt on the bottom run WU, which is given by this formula which is there on PSG 9.18. So let's move to PSG 9.18 first. So this is PSG 9.18 and here we have formula of it. Now remember there is a plus minus signs here. It is clearly mentioned that minus for conveying down and plus for conveying down. So in the previous formula we have taken plus because here it is conveying up, and here we have taken minus. Why is that so? Because minus is for conveying down. So from the formulas you can check for plus or minus. So we got all the values for W also, and we can directly calculate it, and it came negative value of it, that is W is equal to minus 221.64 kgf. Now we can calculate for effective load, which is addition of these two. So as you can see it here in the PSG only, that effective load it is equal to WO plus WU. So similarly we are putting it here, effective load is equal to WO plus WU, which is equal to 1216.89 kgf. So this is the actual load that is on the belt. Now next we have it the motor power. So for motor power we have a load. Now we are going to calculate, we are going to simply multiply it by velocity. So the motor power we have 1216.89 and the velocity we have already calculated, the actual velocity that was 1.52. Now here we got the value of 18 18,496 watts, which is equal to 18.5 kilowatt. And from PSG 5.124 we can select the standard motor of it. Now the thing is, here we got the value of 18.4, so as you can see it here, it will be 18.4 kilowatt. So the standard value of the motor, available motor, will be 18.5 kilowatt, so that we have selected it here. Now next is step 3, that is force analysis. Now in this we are going to check for the tensions in each side. So as you can see here, this we have drawn a diagram, and the similar there are two diagrams on the PSG. Now here you can see there is a drive pulley and this is the driven pulley. Similarly, as you can see it here, okay, now similarly you can see it here, there is a driver member and this is driven member. Similarly here we have a driver member. So we are going to check the diagram similar like this. So we have copied this diagram, this one. So as you can see it here, there are T1, T2, T3, T4. So similarly we have T1, T2, T3 and T4. So the driver pulley is this and driven pulley is this. The total distance is L. Delta is the inclination angle. This is the delta inclination angle. So these are the things. Now we are going to calculate these values only. So let's begin. Now assuming coefficient of friction between the belt and pulley is 0.25 and theta is 200. So these are two assumptions we made. Now after that we are going to calculate T1 by T2, that is e raised to power mu theta. So here we are going to get the ratio of T1 and T2. So this is T1 and T2, that is 2.39 T2. Then we are going to check for power. So power is equal to T1 minus T2 into velocity. So from that we are going to get one equation because the power and velocity is known to us. So it will be T1 minus T2 is 1217.11 kgf. So this is the second equation, we got it. Now next we have T2 and T1 values. We have calculated T2 and T1 values, and from the T2 and T1 values we can calculate T3 and T4. So here we have T3 is equal to T1 plus T1 plus WU. The W is already calculated by us. Now T1 is 2092.7, so we have taken it, so we got T3 also. Now regarding T4, so as you can see it here, regarding T4, here we have values. So T4 is equal to T3 only. So here the T4 value, which is equal to T3, so it is similar like this. So this was regarding the force analysis or the tensions in the belt. Now next we are going to move for the traction element. Now for traction element we are going to study about the belt cross section. Now in belt cross section we are going to assume few things. Number one, it's a belt. In width, B stands for width of the belt. It has some plies layers. So the first layer is TT, thickness, then TI, then TB. So these are the three things. So TI stands for total thickness of a ply, and TP stands for top thickness, TT, and bottom thickness, it is TB. So the first TT, it is ply, TI is ply, then TT is top thickness, and TB its bottom thickness. So it stands for top, it stands for bottom, and in between it is ply. So this is the thing. Now let's move to number of plies. So for that we will have to go to PSG 9.8. So we are there on PSG 9.18. Now this is the formula for number of plies, that is I. I stands for number of plies. Now here we have the formula T1 by B into friction, the working tension, the working tension. Now the thing is, for density of 0.7 ton per meter cube and belt width of 800 millimeter, we are going to check for F value. Why is that so? Because T1 and B value is known to us. So we are going to check for F value, which is on PSG 9.21. So let's move to PSG 9.21. So this is PSG 9.21. So from this page, we are going to check it, that what is the value of F now. So here we have table 5, and from this we are going to take the value of F. Now here we have selected 32 OZ vulcanized joint as a gravity take up. Now this is gravity take up, so it is 0.62 value for F, so that we have written it here, 0.62. Now once this is selected, the I is equal to 5. Now the thing is, we are going to check it for maximum and minimum plies also. So for that we will have to go to PSG 9.21 only and on table number 4. So this is the table number 4, we have it. Now we have standard belt width, that is 800. So here you can see minimum and maximum values of plies. Now we have taken 32 OZ vulcanized joint. So here we have 32, here we have 32, here we have 32, here we have 32. So there are 4 things. Now out of that we are going to check it, that which we are going to select. Now here the density conveyed of the material is 0.7. So in between this range we are going to find out. So this is the right value for us, not these values. So it is 4 and 8. So it is 4 and 7 for 32. So it is 7 and 4. So from table 4 we have selected that minimum number of plies are 4 and the maximum number of plies are 7. So whatever we have taken the value, that is 5. So it is right, it is standard one. Now let the thickness of each ply, this is the assumption, let the thickness of each ply is equal to 2 mm for the fabric strength of 400 Newton per mm square. Now Ti, it is total thickness of ply is 6 into 2, that is 2 mm thickness of each ply, which is equal to 12 mm. Now the top thickness, it is 2 mm, the bottom thickness, it is 1 mm, the total thickness, it is 15 mm. So these are few values that we have assumed it. So on the basis of the assumptions we have selected these, and the total thickness we got it as 15 millimeter. Now after that we are going to start with idler design. So here you can see the truffling idler assembly. So there are 3 roller systems. So the most commonly we use 3 roller system only. So this is its diagram, general diagram, and the belt is here so that the material will be conveyed easily. Now to prevent the belt from sagging due to gravity and under the load, a number of idler rolls between the terminal pulleys. The most common configuration for rollers is 3 rollers of equal length. So this is important. We use 3 roller system which is having equal length. Now we are going to start with the troughing idler. So let's move to the troughing idler. There are 2 idlers, troughing and return. So first we will calculate with the troughing idler. So this is the troughing idler. Now let's start with troughing idler. We have assumed a material C25 and sigma B as a 60 megapascal. Now shape is tubular and provision for the bearing block. Now let's start with the belt width. The belt width is B is equal to L plus 2L minus 100. So from this we are going to check for length of troughing idler. Now it depends on the belt width, so that is why the belt width, standard belt width is 800. So there are 3 idlers, so that is why here going to be we are going to use 300 millimeter, that is length of troughing idler. Now after that, assuming the size of troughing idler, it is 140 mm as a diameter. Now the total number of troughing idler system, that L divided by spacing. So for troughing it is 1.5 because it is carrying the actually load. The material is going to be conveyed over it, so that is why the space should be lesser. Now when it is there is no load on the belt, then there should be a greater space. That 3 meter we are going to take it for the next one, returning idler. Now as these are troughing idler, so that is why the space is 1.5 only. So as per that we need 60 number of troughing idler for this whole system. Now the total number of troughing idler, it is 3 into 60, that is 180. Now as we are dealing with this, the 3 roller system, so that is why we have calculated for 1. So here we are going to total take 180 number of troughing idlers, because each this 3 roller system has 3 rollers and we need total 60. So 60 into 3, that is 180 number of troughing idlers we need it, and those idlers are of equal length only. Now the total weight acting on the troughing idler, it is equal to W dash, which is equal to GG plus GB plus GRO star spacing. So all these values we have already calculated, so we are going to replace it into spacing. Then we are going to get the value, that is 105.7 kgf. Now the middle idler, as we have already seen in the previous diagram, so this is the 3 roller system, and here the belt is going to be kept. So as you can see here, the middle roller, this roller will take 70% of the load. So that is why W is equal to 0.7 into 105.7, that we got it 740 Newton. Now WO, which is equal to the same one again, the 40.21 plus 12 plus 18.25, which is equal to 70.46, that is 0.7046 Newton per mm. Now L1 is 300 millimeter and L2 is 200 millimeter, that we are going to assume margin for the bearing block. Now this is the idler cross section, this is just SFD. Now we are going to check for the calculation for maximum bending moment. So it is WO into L1 square by 8 minus W2 into, sorry, W by 2 into L2 by 2. So L1 L2 we have already assumed now. So here we are going to get the maximum bending moment, that is 29073.25. Now assuming the thickness of idler as 2.5 mm. Now here DO it is 140 mm, DI it is 135, DS is axle diameter, that is 30 mm, then DB it is bearing outer diameter, that is 47. Now here you can select this data from the bearing chapter, that is chapter number 4, for the bearing which is having 30 mm diameter. Now we are going to calculate for induced bending stress, so it is M by Z. So M we have already calculated, maximum bending moment. Now DO and DI we have already taken from the bearing catalog, and this is the value. So it is 0.797, which is lesser than the permissible one. So hence, in case of a bending, the design is safe. Now we are going to move for the returning idler. Now we have done it for troughing. Now we will go to the returning idler. For returning idler, the material load is not present, hence assumed as safe under different failure. The bearing and the bearing selected for troughing idler can be used for returning idler also. So for returning idler, the length of returning idler is L2, which is equal to B plus margin. So B is 800 and the margin we have taken 100. So it is equal to 900. Now the returning idler has diameter similar, that is 140 mm, and the length is 900 mm. Now the total number of returning idlers we need it as 90, total distance divided by 3, that is 30. Now the thing is, here we don't have three roller system, it is only a single roller system. Why is that so? Because at the returning time there is no load on the belt, so that is why only single roller is enough for lifting that load or the bearing that load. So that is why here we haven't multiplied by 3. So it is simple, we need 30 returning idlers. Now next we are going to move for step number 5.3, design of bearing of idler. Now the bearing inner diameter 25, we have assumed it. Now the forces acting on the bearings are, first is a radial load, so that is W by 2, which is W is actually 740, we have already calculated, which is equal to 370. Now axial load, there is no axial load, so that is why it is 0. The assuming working at a room temperature and the nature of load as a medium shock and the life in hours is 15,000 hours. So we are going to calculate as usual the P equivalent load. It is XVFR plus YFA into S. Now here again FA is 0, so only it will be XVFR into S only. So X we are going to take 1, V is equal to 1.2, S is equal to 1.2. Then we are going to calculate for equivalent load, which is 532.8 Newton. Now after that we are going to calculate for RPM N. So V is equal to pi dn upon 60. Now we have just got the value of n here, so we have reversed the formula and we will get n is equal to 207.35 rpm. Now next we are going to calculate for life in million revolutions, so it is life in hours into rpm into 60 divided by 10 raised to power 6. So from this we have got 186.62 million revolutions. Now as it is a ball bearing, so we are going to assume k is equal to 3. Now from equivalent load we are going to check for the dynamic capacity. So the dynamic capacity is equal to C is equal to P equivalent into life in million revolutions raised to power 1 by k. So the k is 3, so that is why C is equal to, we will get this value. Now on basis of this we need to go with deep groove ball bearing as it is having higher rpm. So from any series you can select it, but here I have selected 6005 with diameter 25 and the outer diameter 47, width is 12 mm and the C value it is 780. So here C value is 304.47 kgf and 780 it is safer for that. So from PSG 4.12 you can select these values. So this was regarding the bearing part. Now next we are going to move for design of axle for the idler. Now this is one's design, and from this design, from this diagram we are going to calculate the force analysis. Now we are going to assume the material for the axle is C25 and sigma b it is 60 Newton per mm square and the crushing is 90 Newton per mm square. Now the axle diameter is 30 mm and the bearing diameter is 25 mm. We have seen it already, bearing diameter. Now we have assumed D2 as 20 mm. Now, as you can see it here, D2. Now let L1 is equal to 200 mm. That is from idler design we have taken 200 mm. Then L2 is equal to rigid support span. That is idler length plus margin plus frame width. So idler length is 300 mm that we have already calculated. Then we have margin. Then we have face width. So it is 326. So we have assuming the frame thickness as 14 mm. Now the load acting here, it will be W by 2, that is 370. Now from this we are going to calculate bending and crushing. So here we have bending, so we are going to calculate bending moment. It is equal to W by 2 into L2 minus L1 divided by 2, so that we have done it. Now it is 8.97, which is lesser than the permissible one, so hence it is safe in bending. Similarly we will go for crushing, so crushing is W by 2 divided by D2 into frame thickness. So we have already D2 value and frame thickness, so it is 1.32 Newton per millimeter square. Now here we are going to check for crushing failure. Now as you can see it here, 1.32 is lesser than the permissible value, so hence again it is safer for crushing failure. So this was up to the step number 5, the axle design. Now let's move to the pulley design. A pulley design, as you can see, this is a cross section of a pulley. The pulleys are necessary in conveyors to change the direction of a belt in vertical planes and to form from endless loop for a continuous motion. Now here we have one empirical relation for diameter of a pulley, so which is given as d1 is equal to k1 k2 into I, where k1 is the factor of a pulley material, which is taken as 1.4 for high tensile strength, and k2 it is factor depends on the angle, which is equal to 100 if it is greater than the angle is greater than 180. So from here we can calculate d1, that is 1.4 into 100 into I, we have taken 5, so it is 700 millimeter. So the pulley diameter can be 700 millimeter. Now next we have tr value, now which is equal to 6 to 8, that is 70 millimeter, sorry 7 millimeter, and tw it is 10 mm. So these are two values we have taken. Here you can see the tr value, and this is tw value, its width and radius, the thickness radius. So these two values we have assumed it. Tr we have assumed 7 and tw we have taken 10 millimeter. Now next we have width of pulley. So for width of pulley it is b1 is equal to b plus margin. So b is our width of a belt and margin we have taken for surface side 100 millimeter. So the total is 900 millimeter. So we know v is equal to pi dn by 60. So from that we have calculated n again. So it is 34.56. Now we are going to next move for the shaft diameter. Now for shaft diameter we are going to assume material that C25, and due to shock loads taking more FOS, factor of safety. So shear stresses we have taken 25 Newton per mm square and sigma b is 60 Newton per mm square. Now from this we are going to calculate torque. The torque, we know P value, we know N value, so all values are known to us. So it is torque is equal to 5,111.75 Newton per Newton meter. Now the bearing span can be taken larger for easy maintenance but to control lateral deflection. The assuming bearing span is 1.25 B1. So 1.25 B1 it is 1125. So the B1 we have already calculated. Now next we have W. So it is equal to load, that is T1 plus T2, and the maximum bending moment it is equal to WL by 4. So from this we are going to get the value of maximum bending moment, that is 8348.34. T1 T2 values are already known to us, that we have already done in belt design. Now equivalent torque it is equal to under root square of T and M square, that is moment and torque. Now from this we are going to calculate now shear, and from here as you can see it, we have calculated ds value. So here it is shear stress, so it is ds value we have taken 126 mm, and ds1 it is 1.1 times of ds, and h1 is equal to dh1. These things you will get it in diagram. So this is the diagram of it. So here you will get these values ds1 and dh1, all these things. So there is one empirical relation for that, we have assumed it and we have solved as per it. Now next we have bearing selection for pulley. So the bearing selection, the bearing is a machine element that constrains relative motion to only the desired motion and reduces friction between the moving parts. The bearing is the conveyor belt system is used between the pulley and shaft. So Fr is W by 2 and W is T1 plus T2, we have already calculated it, and Fa as usual it is 0 because there is no axial load. So P equivalent we are going to calculate with the formula P XVFR plus YFA into S. Again the FA is 0, so only XVFR into S. So XVFR into S, this is this value. Now we are going to assume the life of bearing in hours, that is 10,000 hours. Now we are going to calculate the life in million revolutions. So life in million revolutions will be life in hours into number of RPM into 60 divided by 10 raised to power 6. So life in million revolutions will be 20.72 million revolutions. Now from this again we are going to calculate dynamic capacity, and from dynamic capacity we are going to select a bearing. So C is equal to P equivalent into life in million revolutions raised to power 1 by K. So here K is value, that is K is equal to 1 by 3 because it is ball bearing. Now here we have got C value, that is 5869.98 kgf, and for this we are going to take for 140 diameter. So on PSG 4.2 we are going to select the value which is having diameter 140 at least, and which is having capacity greater than 5869.98 kgf. So it is the bearing SKF 6028, which is having the diameter 140 and the dynamic capacity it is 8600 kgf. Now here we are going to start with snub pulley. Now the snub rollers are used to increase the angle of a contact between the belt and the driving pulley and to improve the torque transmission. Now actually if you will increase the contact between the belt and the driving pulley, then the more grip will be created, and because of that the transmission will be in a better way. Now these are used to decrease the distance between the belt carrying side and the return side. It also improves the belt tracking with adjustable snub rollers. Now it is located at the slack side of the head pulley, and the construction features and the material is exactly same as a head pulley. So the diameter of a snub pulley it is equal to 0.6 diameters, 0.6 times the diameter of head pulley. So we have already calculated the head pulley diameter in the previous step. So from that you can calculate the value. Now checking for arresting mechanism. Next we are going to move for PSG 9.18, and here we have WO value. Now you can check the WO value over here, but the thing is, as it is, we are going to use it for conveying down. So initially we have used for the plus sign. Now here we are going to use negative sign. So this is WO, that is why it came negative. Now initially we have calculated the same formula, but it was positive value, but here we have taken positive sign. But now we are using negative sign as it is conveying down, it is clearly mentioned here. After that we will get it negative value. So since W0 it is negative, so if the motor stops working, the belt will move in the opposite direction, and that we don't want. So hence there is a need of arresting mechanism so that it will stop moving of the belt. So for that we need a tension take up unit, and this tension take up unit can be used like this. Now the tension take up unit is required to maintain the tension in the belt, and the simplest form of it is the gravity load. Now to determine the tensioning weight required with 180-degree arc of a contact, using the relation is TR is equal to 2 times T2 minus TTR. Now T2 it's the slack side tension that we have already calculated, and the TTR it is weight of tension roller. Now let's move to its construction, that how it is. Now, as you can see it here, there are two pulleys here, and here it is conveyor belt. This is the conveyor belt, and here we have a slider. This is the guide post where it can slide, so it will slide on this only. Now next we have take up pulley. This is the take up pulley, and this is the counterweight. So according to the requirement it will move up and down. Okay, now for getting the weight we can calculate simply tension. It is 2 times of T2 minus TTR. Now T2 we have already done with this, and TTR we are going to assume it, that is 50 kgf. Now here the tensioning weight required it is 1701 kgf as per the calculation. So this much weight is required for tension take up unit. or tension take up system. So this is the last step of our belt design. So here the design completes. So if you have any doubt, you can ask. Thank you.